All right, so we're going to go ahead and we're going to take a look at this motion graph worksheet here. Make sure we understand the significance of the different type of graphs as we go through. So the first one we're going to talk about is distance versus time graph. So there's a few things we want to keep in mind. I'm looking right here. These remember, motion is a change in position measured by distance and time. Speed tells us the rate at which an object moves. Velocity tells us the speed and direction. So this one is a scalar, while this one's a vector. And acceleration tells us the rate, speed, or direction changes. So we talked about this on the PowerPoint, is that velocity is speed and direction. So if we change one of those, we're changing our acceleration here. So if we start off with our distance versus time graph, we got to keep in mind that the independent variable, that's the one that's not changing. So that's time in this case, always goes on the x-axis. So whether it's an acceleration versus time graph, a velocity versus time graph, or a distance versus time graph, time will always go on that x-axis down there. While the dependent variable, what we're measuring, will go on this y-axis right here. So we got distance versus time right here. If an object is not moving, right? So this is the same distance, and it doesn't matter as time increases. So I start time equals t equals 0, and let's say I go to like the 10 seconds, my position might be at 5, right? And as time increases, I stay at 5. So this is representing a horizontal line, represents an object at rest. Okay, so this is a nice, easy one to remember here. A nice horizontal line on a distance for a time graph means something's not moving. It's staying at the same position. No matter what the time is, it's always at that same spot. Now, if I want to say, look at this relationship here, right? So I would say as time increases right here. So as time increases, what happens to my distance? Well, my distance is increasing. So what's going on? I must be moving at a constant speed. So I'm going to give it some arbitrary value here of, let's say, 5 meters per second, right? After 1 second, let's say that's right here, it's gone 5 meters. After 2 seconds, it'd be 10 meters, right? 3 seconds, 15. So we see this nice linear relationship going on here. This slope of a distance versus time graph is telling us what that speed is. All right. So if we go ahead and look at two different slopes, all right, I got this straight line right here and a dotted line. I can go ahead and calculate which each of these speeds. So this would be the rise over on here and the rise over on here. Well, if I go, let's say, start with this t and go up and say that time equals 1 second right here. Well, this one might have moved some arbitrary distance right here, but this one's almost gone twice that, right? Twice as far in the same amount of time. So what we see is that the steeper the slope, the faster the speed here. So it's really important that you can recognize that and looking at the slope and saying, oh, comparing speeds, seeing which one's faster and which one's slower. Also, what we could have is we could have a negative, right? Instead of my slope being positive, right? Rise over run. If my rise is negative, that just means I'm moving backwards, okay? And then the last one we need to talk about for distance versus time graph is an acceleration. Now, remember, acceleration, we talked about this from the PowerPoint, is that change in velocity. So I'm increasing or decreasing my speed. Well, if I'm increasing my speed over time, I'm going to go faster, right? And if you go faster, you're going to be covering more distance. And so what this does is each time interval, I'm covering more and more of a distance, right? So that's where we see this growth that's showing more and more distance as time progresses. So as time progresses, I'm covering a greater and greater distance here. Okay, and this is key. What we're really looking for is this parabolic shape. Now, if it was accelerating in the negative direction, or we call that deceleration here, that would see a negative parabola. So parabola facing down. But if we see a parabola facing up, that means I'm accelerating going upwards, right? So the key is anytime you see a curve on a distance for a time graph, that's going to indicate that there's some type of acceleration going on. So we can summarize this. This has a nice summary for us right here. Okay, so anytime we see a slope, okay, that tells us that it has a constant velocity, right? A non-constant velocity means there is some type of parabolic shape going on here. If it's flat right here, that means it's just not moving for that time interval. And then we have a downward slope right here. That means we're returning to our initial spot and we have a negative velocity, right? A negative just meaning we're moving in the opposite direction of the positive, right? So this is moving forward. This is moving backward right here. So these are the main things that you have to know from a distance from time graph. Now there's some questions we're going to go over and make sure we get these here. Okay, so this one says, examine the graphs below. Which of the graphs shows that one of the runners started 10 yards further ahead of the other? So which of these graphs, we're looking at these 4 graphs. So we got A, B, C, and D. Which one of these shows that the runner start 10 yards in front of the other? So really don't care about any other position on this graph except for t = 0 because we want to know where they start. What I'd recommend is take a moment. I would say pause this video and see if you can kind of look at these 4 graphs and see if you can figure it out. All right, hopefully you've been able to go ahead and look at them and kind of evaluate. So what I'm going to do is I'm going to go through each 4 of these graphs here and evaluate at t = 0. So we got t = 0 right here. So that's where the y-axis, the x-axis is at 0 right here. At this point, both the runners are starting at 0, 0, right? So that's not 10 yards apart. That's starting at the same spot. So it's not this one. At this one, right, I got 20 and 0. So these ones, they're starting at 20 yards apart. So it's not that one. Now they end at 10 yards apart here, but they're starting at 20, so not that one. Here, again, they're ending at 10 yards apart, but that's not what we want. And here they're ending 10 yards apart, but again, they're starting at the same spot, so that's not the one we want. Here, graph A, we have one runner starting at 0, the other running starting at 10. So each of the line is representing one of these runners, and we can go then show that they're starting 10 yards apart here. So I'm going to go ahead and write graph A here. And because one runner is at 0 and the other is at 10 yards at time = 0 seconds. Okay, so we just look for this part. We're just looking at that t = 0 right here. If you want to get a second, go ahead and get that down. All right, so then let's go to this part. In which of the following graphs below are both runners running at the same speed? Explain your answer. So really to understand this, we got to remember what speed is, right? So I'm going to go down here, and I'm going to say speed is equal to distance over time. So if I want to keep that in mind, that distance over time, I'm going to be comparing 2 things. I'm going to compare the distance that each of them goes over the time that each of them goes. Well, if I look at all 4 of these graphs, notice that the time for each of these runners, right? I got 2 runners here, 2 runners here, 2 runners here, and 2 runners here. For each of these times, they all go from 0 to 4 seconds. 0 to 4, 0 to 4, 0 to 4. So what that means is that I really don't have to worry about the time. I need to take a look at where the 2 runners cover the same amount of distance, right? So technically, this is the change of distance. So D final minus D initial. I really don't care if they start or end in the same spot. I just care they cover the same amount of distance. So I'm going to go ahead and look at this graph right here. So they're starting right here at 10 yards apart. I got runner A and runner B. I'm just going to call them, right? Well, in 4 seconds, this runner covers 30 yards, right? It went from 10 to 30. But this one only covered 10 yards. It started at 20 and ended up at 30. So these are definitely not the same speed. This one had to run twice as fast because it was covering twice the distance in the same amount of time. So it's not this one. All right, let's look at this one right here. So I'm going from, both of them are starting at 10, but now they're ending at different spots. So this couldn't be it either because this one has to be traveling faster to cover greater distance. All right, this one right here. So I'm going from 10 to 20. So I'm covering 10 yards in 4 seconds. And this one I'm going from 20 to 30. So here I'm covering 10 yards. So even though in this case they're starting at different spots and they're ending at different spots, they're both covering 10 yards in 4 seconds. So if we take 10 yards divided by 4 seconds, that could be 2.5 yards per second. They both would have the same speed here. So it'd be this graph right here. So I'm going to go ahead and write. Now notice here the letters get a little mixed up. This is A, B, instead of going C, this is D and then C. So I'm going to say graph D because both runners go 10 yards in 4 seconds, which would be 2.5 yards per second. Okay, so we go ahead and we got that one right there. It's this graph right here. All right, let's go ahead and take a look. So this one, what it does is it wants us to take a look at these descriptions. We got 4 descriptions, 4 graphs. It wants to match the description with the graph. So let me go ahead and just show you what I mean here. I'll do the first one, and I want you to try to do the next 3 on your own. I'm going to start with graph A matches which description. So let's take a look at what graph A. I think it's always easier to write what's going on first. So for graph A, I'm just going to write what's going on. And I always start with as time increases, because we're looking at what happens as I go across this axis right here. So as time increases, what happens? Distance increases. So as time increases, distance increases. Okay, well, what does that describe here? We got 4 descriptions. The car is stopped. The car is traveling at constant speed. The speed of the car is decreasing. The car is coming back. Well, the car's not stopped, right? That would be the same distance. The car is traveling at a constant speed is what we're looking for right here. Because as time increases, it keeps covering more and more distance. So as time increases, distance increases. That's what we call a constant speed. That was the definition we used before. So I'm going to go ahead and put in description 2 right here. All right, so what I want you to do is go ahead and pause the video and fill out the rest of these 3, and then go ahead and resume it, and we will go over those. All right, hopefully you had a second to go over those. I'm going to go, let's look at graph B right here. So I'm going to go ahead and put in this description as well. So as time increases, always start with that. So I'm evaluating what happens as I move across my time. Well, my distance is decreasing, okay? So if my distance is decreasing, well, what's going on? I must be moving backwards. So that's going to be description 4 here. So as time increases, the distance decreases right here. And that's going to be the car is coming back, right? If the y-axis is distance, so y equals 0 is right here. So it's obviously moving back to y equals 0 right here. So that's going to be description 4. All right. Next, I'm going to go ahead and